Hello everyone, welcome back to my YouTube channel. In this week's video, we are going to discuss 8 different questions which cover chapter 4 and chapter 5. So let's get started. Question number 1. Determine the entropy of mixing when 3 moles of hydrogen gas and 3 moles of oxygen gas are mixed together in a container. The first thing that you need to do in order for you to answer this question is to calculate the mole fraction of both gases. Now we are going to start with calculating the mole fraction of hydrogen. So the mole fraction of hydrogen should be equivalent to the number of mole of hydrogen gas, which is 3, divided by the total number of mole, so 3 plus 3, because this one is 3 mole as well. So therefore you will get 0.5. So we are going to do the same thing for oxygen gas. So the mole fraction of oxygen gas is the same, apparently it's the same, so you shall get 0.5 as well. So in this question, you were asked to calculate the entropy of mixing. So the entropy of mixing, delta mix S, is equivalent to negative NR to the summation of mole fraction ln mole fraction. So since we have 2 different gases, so we are going to do the mole fraction for each gases. So it's a summation of that. So from here, N is the total number of moles, since we have 3 moles of hydrogen and 3 moles of oxygen, so the total number of mole is equivalent to 6. And your R is the Cass constant, so it's going to be 8.314 joule Kelvin per mole. And then you're going to do the summation of the mole fraction. So what we are going to do is 0.5 ln 0.5 plus 0.5 ln 0.5. Right? So from here you shall get negative 6 times 8.314. So the summation of this is equivalent to negative 6.9314 times 10 to the power of negative 1. So you're going to do the multiplication of these, so you shall get 3.4577 times 10 to the power of 1 joule per Kelvin. So this is the final answer for the first question. Let's move on to question number 2. At 448 degrees Celsius, the Kc for the reaction between hydrogen gas and iodine gas is 51. Predict how the reaction shall proceed to reach equilibrium if the initial concentration of hydrogen iodide, hydrogen, and iodine gases are 1.0 times 10 to the power of negative 2 molar, 5.0 times 10 to the power of negative 3 molar, and 1.5 times 10 to the power of negative 2 molar respectively. The first thing that we need to do is we need to be able to write a balanced equation for this reaction. The reaction is between hydrogen gas and also iodine gas. So you need to write hydrogen gas reacted with iodine gas shall produce something. So you only have Hi, right? So it means that you're going to have the hydrogen iodide. So in order for you to balance this equation, you need to put 2 around here so that the number of hydrogen and iodine at both sides are equal. Okay, the next thing that we need to do is we need to find the value of Qc, because you were given the initial concentration. So the only thing that you need to calculate is the Qc. So in your Qc, you will have hydrogen iodide to the power of 2 divided by hydrogen gas times iodine gas. Alright, And from the question as well, you were given the initial concentration as such. So please remember that you need to read again the question so that you don't get mixed up. So first one is for hydrogen iodide. So indeed that this is the first value that we need. So we are going to plug in 1.0 times 10 to the power of negative 2 to the power of 2. And then we are going to move on to 5.0 times 10 to the power of negative 3. And the last one is 1.5 times 10 to the power of negative 2. So from here, we will get your QC is actually equivalent to 1.3333. Okay, let's check on the question. It states here that the KC is 51. So we're going to write KC equivalent to 51. And your QC is equivalent to 1.3333. Therefore, your QC is actually smaller than your KC. So once your QC is smaller than your KC, it shall proceed to the right. So when it proceeds to the right, it shall form more product. So you might also want to say that this reaction is a product favored reaction. Right, so this is the final answer for the second question.
Let's move on to question number 3. Sulfur dioxide gas and oxygen gas was reacted to produce gas X in a 1.8 liter vessel. The reaction was conducted at 585 Kelvin until it reached equilibrium with a total pressure of 5.33 atm. At equilibrium, 0.05 mole of sulfur dioxide, 0.08 mole of oxygen gas, and 0.07 mole of gas X are produced. Determine the Kc of the reaction. Right, so the first thing that you need to do is you need to know what the reaction should be like. So the reaction is between sulfur dioxide and also oxygen gas. Therefore, we need to write the balance equation for this. So basically what you're going to do is you're going to write sulfur dioxide, which will react with oxygen gas. So sulfur dioxide is in gaseous form and oxygen is in gaseous form. So you need to predict what is the product. So we only have sulfur dioxide and also oxygen. So basically the product shall be sulfur trioxide. Alright. So after that, what we are going to do is we are going to balance out this equation. Here you have 3 oxygen and here you have 2 oxygen. The easiest way is to write 2 here and then hold on with this oxygen. So 2 times 3 is 6. So you have 2 and 2 over here. So 2 plus 2 is 4. So what are you going to do to make it 6? So you can times 2 over here. Why I times 2 over here instead of at oxygen? Because here when you look at sulfur, you shall have 2 sulfur and therefore you need to have 2 sulfur here as well. So this is your balance equation. So the next thing that you need to do is we are going to write the number of mole. So the number of mole for sulfur dioxide is 0.05, for oxygen is 0.08, and lastly for gas X, which is sulfur trioxide, is 0.07. Then, since we have the number of mole, we need to calculate the mole fraction. So the mole fraction is equivalent to, we are going to do one by one, so 0.05 divided by the total. So you just have to write this one, 0.05 plus 0.08 plus 0.07. So this one should be equivalent to 0.2. So here you need to divide by 0.2. Same goes 0.08 divided by 0.2, and here is 0.07 divided by 0.2. So now you just have to press your calculator and you will get the mole fraction should be equivalent to 2.5 times 10 to the power of negative 1. So here is 4.0 times 10 to the power of negative 1, and the last one is 3.5 times 10 to the power of negative 1. Alright, so if we look closely at the question, it gives us the total pressure, which is 5.33. So basically, from the mole fraction, we can calculate the partial pressure by multiplying with the total pressure that we have from the question. So for the partial pressure, what we are going to do is this value, we are going to times with 5.33. So here is the same, times 5.33, and here also times 5.33. Therefore, you will get your partial pressure equivalent to 1.3325. The other one is 2.1320, and the last one will be 1.8655. So since you already have your partial pressure, so the easiest way is you need to calculate your Kp beforehand. Okay, so from here we are going to calculate your Kp. So your Kp should be equivalent to whatever in the product. So we have partial pressure for SO3 because you have 2 around here. So you need 2 to the power of 2 divided by your sulfur dioxide. So you have sulfur dioxide here. Since you have 2 also, you need to do to the power of 2. And lastly, the partial pressure for oxygen gas. So now you just have to plug in these values that you have already calculated just now. So SO3 is equivalent to 1.8655. So here to the power of 2 divided by 1.3325 to the power of 2, and then times 2.1320, right? So you will get your Kp equivalent to 9.1929 times 10 to the power of negative 1. So this is your Kp. But in the question, you were asked to calculate the Kc of the reaction. So we need to write the Kc by relating with the value of Kp that you have already calculated. Alright, so we are still looking at this balance equation. So from here, what we are going to do is we need to calculate what is your delta N. So since that all of these are in gaseous form, so whatever in the product, so you have 2 in the product minus whatever in the reactant. So we have 2 sulfur dioxide and we have 1 oxygen. So it's equivalent to 2 minus 3. Therefore, you will get your delta N is equivalent to negative 1. So, how are you going to relate the Kp with the Kc? So, the formula is Kp is equivalent to Kc RT delta N. So, for the delta N, you already calculated just now. Your delta N is negative 1. And your R is the gas constant. The temperature is given to you in the question, which is 585 Kelvin. And now it's easy for you to find your Kc. So what I'm going to do now is I'm going to rearrange this formula so that we can get your Kc. So Kc is equivalent to your Kp divided by RT to the power of delta N. So all of this value is already calculated. So Kc is equivalent to your Kp, 9.1929 times 10 to the power of negative 1 divided by your R. So your R is the gas constant, 0.0821, and your T is the temperature given in the question, which is 585, and the delta N is equivalent to negative 1. So you shall get your Kc is equivalent to 4.4152 times 10 to the power of 1. So this is the final answer for the third question. Moving on to question number 4. A certain reaction has an equilibrium constant value equal to 0.0260 at 25 degrees Celsius and delta H equivalent to 32.4 kilojoule per mole. Determine the suitable temperature to conduct the identical reaction to ensure that the equilibrium constant is equivalent to 4.3133 times 10 to the power of negative 2. So this is a rather straightforward question. We can use the formula of ln K2 over K1 is equivalent to negative delta H divided by R, which is the gas constant, times 1 over T2 minus 1 over T1. Right now, what we are going to do is we are going to look at the information given to you in the question. So the question gives you the value for the delta H, which is 32.4, and then the equilibrium constant, which is your K1, is equivalent to this, with the temperature 25 degrees Celsius for T1. And then the question also states that you want your equilibrium constant for your K2 equivalent to 4.3133 times 10 to the power of negative 2. Alright, so now we are going to plug in all the values that we already have. So ln K2, so your K2 is 4.3133 times 10 to the power of negative 2. And your K1 is 0.0260. And then your delta H is equivalent to 32.4 kilojoule per mole. Therefore, your value of R should be 8.314 joule over mole per Kelvin. And then the T2 is the one that you are going to calculate, and your T1 is equivalent to 25 degrees Celsius. So you write here 25, but you look at here, your gas constant is in Kelvin. So you need to convert this to Kelvin as well to 73. So from here, what you are going to get is 5.0619 times 10 to the power of negative 1 is equivalent to negative 3.8970 times 10 to the power of 3 times 1 over T2 minus 1 over 298. So you're just going to do a simple calculation. You will get 1 over T2 is equivalent to negative 1.2989 times 10 to the power of negative 4 plus 1 over 298. Therefore, your T2 should be equivalent to 310 Kelvin. So from this 310 Kelvin, you can calculate back to degrees Celsius. So 310 minus 273. So you shall get 37 degrees Celsius. So this is the final answer for the fourth question. Question number 5. What is the pH of 0.2 molar of ammonia solution at equilibrium after the dissociation process if the Kb for ammonia is equivalent to 1.8 times 10 to the power of negative 5? Alright, so the same drill as other questions. The first thing that we need to do is we need to write a balanced equation for this dissociation process. So there's a clue here in the question. It states here that this is an ammonia solution. So this is a clue for you. If it's a solution, means that we need to add water. So ammonia and H3, you need to add water. Hence, it shall dissociate into NH4 positive plus OH minus. So from here, we can write our ice diagram. So ice diagram, The initial concentration of ammonia is given to you, which is 0.2. So you are going to write 0.2 here. At first, there's no dissociation. So bear in mind that although we add water here, but the water shall not do anything to your ice diagram. So at change, here will be minus x, here will be positive x and positive x. So at equilibrium, it's going to be 0.2 minus x, x, and x. And then given to you the Kb is equivalent to 1.8 times 10 to the power of negative 5. Therefore, you need to calculate your Kb is equivalent to x times x divided by 0.2 minus x, whereby your Kb is 1.8 times 10 to the power of negative 5 should be equivalent to x squared divided by 0.2 minus x. So here we are going to do approximation method. So you will get 1.8 times 10 to the power of negative 5 is equivalent to x squared divided by 0.2. Therefore, your x squared is equivalent to 0.2 times 1.8 times 10 to the power of negative 5, whereby you will get your x is equivalent to 3.6 times 10 to the power of negative 6. So you need to square root this, and you will get 1.8974 times 10 to the power of negative 3. So since this is an approximation method, we need to know whether this value of x is valid or not. So we need to do the test check. Alright, so in order for you to do the test check, so test is equivalent to the value of your x, which you have calculated just now. So it's going to be 1.8974 times 10 to the power of negative 3 divided by initial concentration, which is 0.2 times 100%. So you should get 0.9487%. So this is less than 5%. Therefore, we consider that the value of x that we get is okay. So it means that we can use this value of x as is. So when you check, this value of x is actually the concentration of OH minus. So the concentration of OH minus is equivalent to 1.8974 times 10 to the power of negative 3. And the question asks you to calculate what is the pH. So what we are going to do now is we are going to find the pOH beforehand. So pOH is equivalent to negative log concentration of OH minus. So negative log 1.8974 times 10 to the power of negative 3 should be equivalent to 2.7218. So since you want to calculate what is the pH, you should know pH plus pOH is equivalent to 14. So your pH is equivalent to 14 minus your pOH. So your pOH is here, minus 2.7218. Therefore, you will get your pH equivalent to 11.2782. So if you want to check, this is an ammonia solution, and after the dissociation you have OH lingering around, means that it should be having a basic properties. Therefore your pH should always be larger than 7. So this is the final answer for the 5th question. Let's move on to question number 6. In an electrolytic cell, a redox reaction is made to occur by supplying electrical energy to the system with 2 electrodes, namely magnesium and zinc. Determine the standard free energy change, delta G, of the reaction if the anode cell is equal to positive 1.61 volt. So for this question, you have two different electrode, which is magnesium and also zinc. So we are just going to write the half reaction for this. So magnesium, it will turn into magnesium 2 plus, and for zinc as well, so Zn2 positive, so you will have zinc minus 2 electron. So this half reaction is very important so that we know how many electrons are lingering around. Therefore, from here we know that your N is equivalent to 2. So since we already know this value of N, so we can calculate your delta G note, which is equivalent to negative N F E node cell. Alright, so your N is equivalent to 2, we have calculated just now, and your F is actually a constant value, which is 96.485 kilojoule per volt. And your E node cell, so your E node cell is given in the question, which is 1.61 volt. So this one you can slash them out, so leaving you with only kilojoule. So you just need to calculate this using your calculator, equivalent to 3.1068 times 10 to the power of 2 kilojoule. So this is the final answer for the 6th question. Question number 7. An antique automobile bumper is to be chrome plated. The bumper, which is dipped into the dichromate solution, serves as cathode of an electrolytic cell. If the current is 21.4 ampere, calculate the duration in hours to deposit 1.72 times 10 to the power of 2 gram of chromium onto the bumper. From this question, you were given the mass of the chromium. Therefore, what we can calculate is the number of mole. So number of mole of chromium is equivalent to the mass over RMM. So the mass of chromium is given to you in the question, which is 1.72 times 10 to the power of 2 gram, and the RMM is equivalent to 51.996. Therefore, you will get the number of mole for the chromium is equivalent to 3.3079 mole of chromium. Right? So what else that is important for you, because you are going to know what is the duration, so you need to have how many electrons are there so that you can convert to coulomb. So you need to know how to calculate the oxidation number. So we are going to calculate the oxidation number for the dichromate. So from the question, you're already given the formula for the dichromate. So you have Cr2O7 and the charge is negative 2, right? You don't know what is your chromium, what is the oxidation number. So since you have 2 here, so it's going to be 2x. So plus, you have 7 oxygen. Remember, for oxygen is always be negative 2. And then the total should be negative 2 as well because of the charge around here. If there's no charge, it's going to be 0. So 2x is going to be plus with negative 14 equivalent to negative 2. So 2x is equivalent to negative 2 plus 14. So 2x is equivalent to 12 and your x is equivalent to 6. Means that your chromium is actually positive 6. The oxidation number is equivalent to positive 6. Alright, so since you already know the oxidation number for the chromium, so it's easier for us to write the half reaction. Since the oxidation number of chromium is 6, so we can write chromium 6 plus 6 electron, it shall produce the chromium, right? So from here, it's really important for us to know how many electrons are involved. So in other words, we can say that 6 Faraday shall produce 1 mole of chromium, right? So we need to rearrange this. So 1 mole of chromium, you needed 6 Faraday, but we already calculated that we have this much of chromium, so therefore 3.3079 mole of chromium is equivalent to 6 times 3.3079. Therefore you will get 19.8474 Faraday. Alright, but you are going to calculate what is the time. So still you need to convert the unit from Faraday to Coulomb. So 1 Faraday is equivalent to 96,500 Coulomb. So you have more than 1 Faraday, have 19 plus, so 19.8474 Faraday is equivalent to 96,500 times the same value, 19.8474. So you will get 1915274.10 Coulomb, right? So we needed this in Coulomb so that we can change it to the time. Okay, so now we can use the formula of Q equivalent to IT. So your Q is this one, so 1915274.10 is equivalent to your I. So I is current given to you is 21.4 ampere, and your T is the thing that you want to calculate. So your T is equivalent to 1915274.10 divided by 21.4. Therefore your T is equivalent to 89498.7897 seconds. But looking at the question, you were asked to calculate in hours. So you need to convert from second to hours. So what we are going to do is we need to convert that. So basically 1 hour is equivalent to 3600 seconds. So 3600 seconds is equivalent to 1 hour. So we have 89498.7897 seconds, so equivalent to 1 divided by 3600 times 89498.7897, so you will get 24.8607 hours, right? So this is the final answer for the 7th question. Alright guys, so we are now at the final question for this week's video. Question number 8. A cell is prepared by dipping a copper rod in a 0.01 mole copper sulfate solution and zinc rod in a 0.02 mole of zinc sulfate solution. The standard reduction potential of copper and zinc are positive 0.34 volt and negative 0.76 volt respectively. Calculate the cell potential, which is the E cell, for this reaction. Alright, so in this question, you were given the standard reduction potential for copper and zinc. So you have one is positive 0.34 and the other one is negative 0.76 volt. Alright, so the main concept that you need to remember is that the more positive the standard reduction potential, it shall be put at the cathode. Apart from that, you should always remember our beautiful red cat. So our red cat, this shows that at cathode, the reduction shall occur. Alright, so let's take a look at the question. So the standard reduction potential of copper is positive 0.34 and the standard reduction of zinc is negative 0.76. So it means that copper, the SRP is more positive as compared to zinc. So the one that is more positive, it should be put at the cathode. So and then the cathode shall undergo reduction, red cat. So your copper should be copper 2 positive plus 2 electrons, which shall produce copper. So your zinc, since this is negative, right, means that it shall go oxidation at anode. So zinc minus 2 electron, it shall produce zinc 2 positive. So now what you are going to write here is the anode cell. So your anode cell here, supposedly for copper, you just have to copy 0.34, but for the zinc, because this is not the reduction, this is standard reduction. Since you already changed it to oxidation, so from negative 0.76, you change to positive 0.76 volt. So therefore, you will get your anode cell is equivalent to the summation of these values. So you just have to add this value together and then you will get 1.10 volt. So this is your anode cell. And you should always write the overall reaction, which is the zinc plus Cu 2 positive to produce Zn2 positive and copper. Right. So since you already write the anode cell, which is 0.76 plus 0.34 equivalent to 1.10 volt. So you can calculate your E cell. So your E cell is equivalent to anode cell minus 0.059 divided by N log concentration of anode divided by concentration of cathode. Alright, so now what is your N? So the N is the amount of electrons in your half reaction. So altogether we have 2 electrons, so your N is equivalent to 2. So the concentration of anode, so in your anode is actually the zinc sulfate, so the concentration is 0.02, and your cathode is copper sulfate and the concentration is 0.01. So we are just going to plug in this value. So your anode cell is 1.10 minus 0.059 divided by 2 because of this. So log concentration is 0.02 divided by concentration 0.01. Alright, so from here we can get the calculation. So 1.10 minus 8.8804 times 10 to the power of negative 3, and at the end you will get your E cell is equivalent to 1.0911 volt. So this is the final answer for the 8th question. Alright, so we have come to the end of this week's video. I would like to thank you very much for watching this video until the end. And if you feel that this video is beneficial for you, please give it a thumbs up and I'll see you again next week. So be good and take care. Goodbye.